Hey everyone, we're back. This video is going to be a lot quicker than the other ones, but I just wanted to give a slight geometric motivation for kind of what we're doing when we're dealing with these partial differential equations. And yeah, I guess that is kind of the long and the short of it, honestly. So right now I'm just going to talk about the Laplace equation. The heat equation, there's a way better demonstration that I could ever do in the video that I linked. The wave equation is very, very similar. My understanding of the wave equation is that it doesn't peter out necessarily like the heat equation does. It kind of keeps going, but if you look up a diagram, it'll look relatively the same. And then that kind of just leaves the Laplace equation. So I thought I'd just go over that super quick and just give kind of a quick understanding that helped me kind of understand what was going on. So as you can see here, we've got a rectangle Laplace equation. You can tell because it's bounded by a rectangle. And I just wanted to kind of show you, so remember our Laplace equation takes the form, it's something like this, equals 0, and then we get some boundary conditions, right? Well, I guess I can just write those out. So something like this, oops. And then it looks like maybe this one is u of a, so y is g of y for some function. And then we get ux0 equals uxb equals 0. Remember, x is going between 0 and a usually, and y is going between 0 and, I guess I could have written this up beforehand. But so basically what we're dealing with here is our g of y is going to be kind of this thing here. It's this side. You can see every other side is 0 along the edge. And then you can't really see it, but on this side it's 0 as well. And then what this partial differential equation is telling us is it's giving us information about how the curvature of this curve on top that you see is kind of is working, right? And so basically the questions we're trying to answer are given some information about the curvature, right? So the second derivative in either direction, which is the x curvature and the y curvature. Given some information about that, what can we say about kind of, in some sense, the shape of this manifold or this sheet that's on top? So, I mean, honestly, that's pretty much all I wanted to say about it. I just wanted to say that it's very easy, I think, to get caught up in the algebra here and not really take a step back and think, okay, like, what are we doing, right? What are we doing? But yeah, that's really what we're doing. We're taking information about curvature in the x, or in the y and the x directions. This should be like that, huh? And we're trying to say something about the surface based solely on boundary conditions. And frankly, I think that's kind of amazing. I mean, all we know is some information about how the derivatives interact, and we know what the edges look like, and we can tell what this manifold is going to look like based off of that. So I just think that's kind of cool. Another classic example is the classic annulus. I won't write the equation down here just because it's on the note sheet. But this is kind of an example of what might happen with an annulus. So remember, we're given 2 radii, so like this would be our R1, and then our R2 would be out all the way out. And these colors on this graph are meant to kind of represent the heights over here. But I mean, you can see, so that in this case, like maybe our bounding function is, so our, oh geez, I can't remember the format. But regardless, basically the boundary function on the outside is clearly some kind of sine wave, right? Since we're moving around this little this ring, and as we move around, we kind of have. In fact, this is a classic example. I got this off Wikipedia. You just look up Laplace equation annulus, you'll get this, and they have a good description of like, okay, like we're bounding it by, obviously it's a constant function on the inside. All of this stays the same height the whole time. But on the outer ring, we define it by some sine wave, and I guess that's important in certain types of analysis. So yeah, I mean, really, that's all I wanted to say. I just wanted to to try and tie in a little bit of a visual representation for those of you that feel like that helps, just for the sake of understanding kind of what this crazy algebra we've been doing, what this crazy calculus we've been doing is actually talking about. And actually in this case, so I guess I could tie this in. So again, we're given boundary conditions, and then we have the same restriction that that this property must hold. So we know that the curvature has to satisfy this property. And then we can say something about the entire shape of the manifold, or when I say manifold, I just mean whatever the surface is. Without, just without information, just based off of what the boundaries look like and how the second derivatives interact, or frankly any derivative interacts. Yeah, I suppose that's it for today. I hope this kind of helps give a better understanding of what we've been working with here. But yeah, thanks for watching.